On most beautiful summer days like today, you can see boats all along the Charles River in Boston. It's a great recreational activity. But have you ever wondered how boats stay afloat? How do large ships and even sailboats float in water, even though they're made of heavy materials? Hi, I'm Andy, a graduate student at MIT, and today I'm going to talk about the concept of buoyancy, which is the upward force produced by the water in the boat, keeping it afloat. How buoyant an object is depends on the density of your fluid, gravity, the shape and size of your boat, and the amount of water your boat's displacing. 1 cubic foot of water weighs about 62 pounds, so for every cubic foot of water your boat pushes out of the way, it'll give it an extra 62 pounds of buoyancy. So even though ships can be made of heavy materials, they can be designed in a way that displaces a large amount of water, keeping it afloat. As long as the weight of your boat is less than the weight of the water it's displacing, it will still float. Let's go to the lab to explain more. So to visualize the concept of buoyancy, we have an object of a certain density floating in a fluid of a certain density. Then we have gravity pulling the mass of the object down, while buoyant forces are pushing it up, keeping it afloat. The buoyancy acting on the boat is equal to the weight of the water it displaces. The boat is designed to displace enough water to keep the people in the boat afloat. Let's do some math.
Hi, I'm Brad, and I'm going to walk you through some of the math related to buoyancy. So, like we talked about before, buoyancy is a force that acts upward. Force, buoyancy. Gravity is a force that always acts downward. Force of gravity. In order for your ship, or your life raft, or your rubber ducky to float, you need these two forces to be equal to one another. So let's look at this from a mathematical perspective. We know that the force of gravity is equal to mass times an acceleration. We know that from Newton's second law. And in this case, the acceleration is the acceleration due to gravity, or g. So we can write this as mass times gravity. To look at the force of buoyancy, we calculated it a little bit differently. It's equal to the density of the fluid in which your object is submersed, the volume of the dispersed fluid, and the acceleration of the local gravity field. So let's try and do a real-life problem to put some of this math to work. And what better problem to analyze buoyancy than perhaps the biggest ship that's ever sailed, the Titanic. So the Titanic set sail in 1912 with 2,223 people on it. And this ship at that point weighed 46,328 tons. If we go back to these equations that we had before, we have mg, which is the force of gravity, being 46,328 tons. We can convert that into a unit that makes a little bit more sense, and that's equal to 92,656,000 pounds, or 412,154,422 newtons. That is a humongous ship. So how do you keep a ship that weighs 412 million newtons above water? The answer, of course, is using the idea of buoyancy. So let's actually calculate. The thing that matters here is how much water did the Titanic displace to keep itself above the surface. And that comes to how much volume underneath the ship, underneath the surface of the water, was actually there at the Titanic. You only see the top of it, but there was a whole lot more going on underneath. And we can actually calculate exactly how much was down there using these simple equations. So we know mass times gravity. This is the force of gravity. Now we need to calculate the force of buoyancy. And that is equal to, like I said, rho times volume times acceleration. Here we know what the density is. The density is the density of the seawater the Titanic was floating in, and that's 1,025 kilogram per cubic meter. And the acceleration is the acceleration due to gravity, which is equal to 9.81 meters per second squared. So now we have all of the pieces of the puzzle, and we need to calculate the volume of the Titanic underneath the water. So let's set all these equal together and actually calculate it. Now go ahead and try and solve for the volume of the underwater part of the Titanic, and we'll check and see if you're right in a few seconds. Okay, you got the answer? So, if we run all the numbers, we get V is equal to 41,000 cubic meters. That's huge. Do you have any idea how big 41,000 cubic meters is? To give you an idea, that would be equal to 46 747s sitting underneath the surface of the water. So when the Titanic was sailing, there was 46 747s worth of volume underneath, keeping it afloat. That's huge. Now that we've done the math, let's actually go and do some experiments to see how this plays out in real life.
Here I'm going to demonstrate the effect fluid density has on buoyancy through an experiment. To do this experiment, you need 2 cups of water, 2 eggs, a spoon, and salt. If I drop the eggs in the cup of water, they both sink to the bottom. These eggs sink to the bottom because they weigh more than the weight of the water they are displacing. You can also see the amount of water the objects displace. When we dropped the eggs in the cup, the water level rose from about 170 to 220 milliliters of water. So each egg displaces about 50 milliliters of water. If, however, you add salt to one of the cups and stir, you are changing the density of the water. By adding salt, you're adding mass. Now that there's more mass in the same amount of water, the density of the fluid is higher. Since the salt cup now has a higher fluid density, the experiment might produce different results. This time, the egg in the salt cup floats. Because we added mass to the water, the fluid density increased. Now the egg weighs less than the water it's displacing, which caused the egg to float. By changing the fluid density of the water, we increase the buoyancy of the egg. This experiment explains one of the reasons why people can float in the Dead Sea, a very salty body, much easier than in a swimming pool or the Charles River in Boston. Changing fluid density is not the only way to change buoyancy. Objects of different shapes and sizes can also affect buoyancy. Now we're going to try an experiment with clay. The ball of clay weighs 1.32 ounces. This boat of clay also weighs 1.32 ounces. Even though both of these pieces of clay have the same weight and density, they have different shapes, so they will displace different amounts of water. Let's see what happens when we add these 2 objects to the water. The ball of clay sinks while the clay boat floats. This is because the clay boat displaces more water than the clay ball, giving it more buoyancy. From these experiments, you can see that changing the fluid density and changing the size of your object can affect the buoyancy. You can try these experiments at home with the help of your parent or guardian, and you can see for yourself which objects float and which objects sink.